Your questions. All right, we're going to close up the day with the last session on water quantity, and I'd like to introduce John Crowley to open that session.
Okay, thanks everyone for sticking around, and thanks to the organizers for all the work you did on this meeting, and for the opportunity to discuss some of the work we've been doing today. So my name is John Crowley. I'm with the Canadian Geodetic Survey in Ottawa, and what I'll be talking about today is using satellite-based gravity changes to estimate and monitor changes in regional and national scale water storage. So I'd also like to acknowledge my colleagues, Zhaliang Huang in the Canadian Geodetic Survey, Hazen Russell and Melissa Bunn in the Geological Survey of Canada, and Steve Fry at Aquanti. And I'd also just like to acknowledge that at least for the last few years, this work has been done as part of the Canada One Water program, which Steve's going to talk a little bit more about in a couple minutes. So I don't think there's any need to discuss the importance of water with the group here today, but as a geodesist and a geophysicist, people are always asking me, what does water have to do with gravity? So my group's responsible for measuring gravity and gravity change across Canada, and it turns out that the largest driver of gravity change across Canada is in many parts due to changes in water storage. So when we're looking at changes in gravity, we're seeing very strong signals associated with water storage change, and we can use our gravity measurements to estimate what those water storage changes are. So the idea is that we can estimate these changes at a national and regional scale, and then provide these kind of independent geodetic constraints to help calibrate and validate regional scale hydrological models. Then in turn, once we have some confidence that the models are working well, we can use these models, which are often much higher resolution than anything we're going to get from satellite missions anytime soon, to then refine our gravity models and other geodetic models that we have. So it's a very nice and interesting kind of mutually beneficial collaboration. Okay, so I always like to spend just a few minutes discussing how this works. So the satellite mission that I'm using is the Gravity Recovery and Climate Experiment mission, or just GRACE for short. This was a joint NASA-German space mission. It consists of a pair of satellites that orbit the Earth at an altitude of about 500 kilometers. So I've got a few cartoons here to kind of explain how it works. So on the left is a little environment that could pretty much be anywhere in Ontario. You've got a lake, you've got some land with some trees, you've got some water in the ground that I kind of tried to show with the shaded blue region, and you've got some snow on the surface of the ground. When these satellites pass overhead, the path they take is partially determined by the local gravitational field. Now, if you move from the image on the left to the image on the right, this is sometime in the future. We now have more water in the lake, more water in the ground. There's more water stored in snow at the surface. So more water means more mass. More mass means a larger, stronger gravity. And so the next time those satellites pass overhead, they take a slightly different path in response to that change in the local gravitational field. So by tracking the path these satellites take, as well as a few other parameters, we can estimate what the associated changes in gravity are, and then figure out what the changes in water were that created those. So in terms of limitations, I mentioned that these satellites orbit at an altitude of about 500 kilometers, so they're quite far away, and this means that we have to work on a scale of about 200 to 300 kilometers or bigger. So unfortunately, we can't go down to the local scale that a lot of people here will be interested in, but it can still be useful at a regional scale. And the other thing is, because these things are 500 kilometers away, they're not at all sensitive to vertical structures. So they can't distinguish between a change that's happening due to snow or surface water or soil moisture or groundwater. What they see is kind of the cumulative sum of all of those changes together. So we call that the total water storage. Now, while there's some limitations in that, in the sense that we can't figure out exactly what's going on, it's also one of the real strengths of this mission is that it is sensitive to and will capture changes in groundwater. So we can use this anywhere in Canada or anywhere in the world, where for most places in Canada, it's very, very difficult to get at groundwater because most of Canada is remote. So that's kind of one of the advantages of this data set. I don't want to go into too much detail on what we do technically, but I do want to say we've been working on this for quite a while. I've been doing this myself almost 20 years, and we've developed several methods at Natural Resources Canada for working with and improving this data. So on the top, I'm showing you 2 monthly solutions for changes in water storage from this mission. Basically red shows regions that have lost water, blue shows regions that have gained water. And in the images on the top, which are what you get if you download the data from NASA, you can see there's a lot of noise and there's a lot of problems with the data. After we apply some of our methods that we've developed, we basically get the images on the bottom where you can start to kind of see those real geophysical signals coming through. And this allows us to kind of, really take advantage of the full potential that GRACE has to offer. Okay, so how do we know if this is working or not? So we used to try and compare our results just to groundwater wells and look for correlations, but that's extremely difficult to do, and you're only getting at part of the problem. But recently, we've been able to start comparing to more detailed hydrological models, and today the model I'll be comparing to is a Quanti's hydrogeosphere for Southern Ontario and in another region I'll talk about soon. So kind of on the left, I'm calling this the modeling approach or kind of the more traditional approach. You've got a 3-dimensional model that incorporates the 3-dimensional geology and structure of the region. And it requires a lot of inputs. So it requires, like I said, the geology, climatological data, well water levels, stream flow data, soil moisture measurements, snow data. There's a lot of pieces that you need to build this model, and a lot of work that needs to go into it. These are very sophisticated numerical models and flow simulations, so they also require significant computational resources. So there's a lot of work that goes into these. On the other hand, on the other side of things, we have this satellite gravity approach. This uses publicly available data that anyone could download. We do one correction that basically corrects for vertical motion due to tectonic processes like plate tectonics and glacial isostatic adjustment. But in most regions, there are pretty good models to account for that. And then we simply apply our methods. We don't need any other inputs or assumptions about geology. And we can apply this method anywhere in the world because it's a global data set. And in terms of computational resources, you can do this on my government laptop, which is not a good laptop, and it takes a few minutes. So this isn't to say that this is a better approach. This is kind of a large-scale approach. The model is actually what's going to give you all the detail, and I'll kind of get to that in a second. So we picked the area of Southern Ontario to kind of do this comparison and validation for a few reasons. One reason is Quanti's got a nice model that they've been spending a lot of time developing, and a lot of work has gone into it, and I think many people here have contributed to that in some way or another. Of course, it's an important region because there's a lot of people living in Southern Ontario. It's in an important hydrological region in the Great Lakes Basin. And technically, it's actually a very, very challenging region as far as GRACE goes, because one, it's small. It's small on the scale of GRACE. So it's actually kind of at the lower limit of what we can expect to do with GRACE. And the other thing that makes it very challenging is, the Southern Ontario region, which is shown in green on the map, is sandwiched right between these Great Lakes, in which you've got significant water level changes going on. And when it comes to gravity, sometimes if you've got adjacent regions with complicated signals, they can kind of leak into your study region. So it's a very challenging region to try this. And here are the results, what we found. And we were very, very happy with this. So on the vertical axis, you're looking at changes in water storage in cubic kilometers, so quite a bit of water. And of course, on the x-axis is time, going from 2002 up to about 2022. The blue line is the total water storage estimated from a Quanti's hydrogeosphere model, and the black is what we get from satellite gravity. So we're seeing a really, really good agreement in these two completely independent approaches. This gives us a lot of confidence that both methods are probably getting pretty close to the right answer. So you can see that we're matching amplitudes pretty well, actually surprisingly well. We did not expect it to be this good. We're getting the timing right. So we're seeing that seasonal trend, and we're also seeing the long-term changes. So there's not a ton going on in this area in terms of long-term trends, but you can see from 2002 up to about 2010, there is an increase of about 5 to 7 cubic kilometers of water. And then after that, the evolution is fairly stable. Yeah, we were really happy to see this result. Now, of course, we can do this with the satellite gravity data, but of course, in the end, most people here want the details. And so, once you know that the regional model is working well, then you go back to the detailed regional model. And so I'm sorry if the text there is a little bit small, but essentially what these other signals are just changes in surface water, soil moisture, and groundwater that come from the hydrogeosphere model. And of course, you can go into much more detail in terms of the spatial resolution and temporal resolution and all of that. Just recently, we were able to try this for another region, a second region. So kind of a second test at this approach. And the region we did it in was the South Saskatchewan River Basin. So Quanti's doing some work for the Alberta government to essentially assess the drought situation there and potentially do some forecasting for them. So they basically gave us their geometry for the region. We processed the data, and again, you can see the comparison here. The blue is the hydrogeosphere result, and the black is the satellite gravity. Again, we're extremely happy with this, and I will say one thing here. This is actually the second solution that we compared to, and the first solution from the hydrogeosphere model actually had some fairly large discrepancies. And so Steve and I kind of sat down to figure out what might be going on, and we looked at the different inputs into their model, and we realized that there was a huge amount of uncertainty in the different snow models that they use. So there's a few different options they have. So we tried a different snow model, and that essentially gave us the results we found here. So this is an example of how this satellite gravity geodetic independent constraint can be used to help improve or calibrate and test regional scale hydrology models. To build a hydrology model like this, like I said before, you need a lot of inputs. You need the geology, you need a lot of other things. For using satellite gravity, we don't need all of that, so we can do this anywhere we want, and we do. So here is the national scale solution. This is a map of trends in water storage across Canada in equivalent water thickness in terms of centimeters per year. So blue regions are regions that have trends that are positive and are gaining water with time, and the red regions are regions that are losing water with time. But I will caution, a lot of people who work with GRACE data, they love to do these trend maps, they publish them, they kind of leave it there, people look at the map and they say, okay, well, my region's increasing or decreasing. Sometimes you can do that. Sometimes, when you actually look at the time series and what's going on in those regions, a linear approximation or a simple trend is enough to capture what's going on, but most of the time it's not. So here's a few other examples for other regions. And if you're just looking at a trend map and you're just saying, okay, well, it's got a positive trend, you're going to miss a lot. So here's somewhere in the Mackenzie that was decreasing at a fairly regular rate, and then just recently the trend is kind of reversed, and now we're seeing an increase. Here's basically changes driven by changing lake levels in the Great Lakes. So these are more or less just showing you what's happening with the Great Lakes, but it's not really at all linear. Here's something in the Nelson. Again, if you were just to look at a trend, a simple trend to that would say, okay, well, water's increasing in the region, but you'd totally miss what's been going on over the last few years, which is probably the really important part, or the interesting part anyway. So I'll kind of just bring it back to these two different approaches and discuss kind of what we envision as the next steps. So for starters, we'd like to continue this work, hopefully under kind of a phase 2 for the Canada One Water program. And we see this as being a bit of an iterative approach. So we can either use GRACE, to identify regions where there's interesting or important things going on, or the hydrological community may already know regions where these important things are going on. So then the modelers go to work and they build their detailed models, and then we use, again, these independent gravity constraints to help calibrate and validate these models. Then once we've got some confidence that things are kind of working well at a larger structure or larger scale, then you can probably start having more confidence in the finer scale features as well. And then yeah, ultimately it's going to be the hydrological models that really help you figure out why these changes are happening. So it's not, I don't see one method being better than the other. I think they work very well together. And in the future, we'd like to use these together, not just to be able to do water forecasting, but also to be able to do gravity forecasting. So we can get higher resolution, spatial and temporal models for gravity change across Canada. Okay, thank you.
Thanks, John. Thank you. We have time for maybe one question, if anybody has one. Burning question, quick one. Oh, we got a volunteer here.
Hi, interesting presentation. I'm not entirely sure I'm with you in terms of the size of the error being small. So you've got, in the two different hydrographs, you've got differences of 5 to 10 cubic kilometers. That sounds to me like a lot. So, and they're not also what's a bit more worrying is that they occur in one place you have a good match and another place you don't. So can you expand a bit more on that?
So I'm not sure I understand the first part of your question. Are you just basically asking whether or not that increase we see in Southern Ontario is significant or not?
Well, the first part is just a statement. As I'm saying, if you look there, you can see differences of say 5 cubic kilometers. It's a lot of water, yep. And they occur in certain places on this hydrograph, but they don't occur in other places. Can you explain that?
Oh. Sometimes yes, sometimes no. So I mean, these are both developing techniques, right? And I guess knowing what goes into it, for me, I'm very happy with these results. But I guess it depends, what your field of study is, and other people might look at these and they might say, oh, well, that's not very good at all. But you have to keep in mind that both approaches, if you're not careful, can be way off. So I mentioned that kind of the first pass at this using SNODAS for the snow model, it was completely different from the geodetic observations, like by tens of cubic meters. Without an independent source like these gravity measurements, you'd have no way to know that you're off. So of course there are still some differences in it, and I didn't want to talk too much because I'm probably already over time, but when we sat down and we looked at these different snow models, they all seem to agree fairly well before 2012. And this is actually where we get a pretty good agreement between the gravity estimates and the hydrological model estimates. And then for whatever reason, kind of after 2012, there's a period where they differ in their estimates of snow by up to like 300%. So the answer you get from the hydrological model really depends a lot on the snow model you use. So, I mean, this is, it's still a work in progress. And I think we're still refining both approaches. If I had to put error bars on the estimates from the satellite gravity for these regions, it would probably be a few cubic kilometers. So we're still going to get the large scale trends and seasonality. And one of the things we were happiest about here is even though there's some discrepancies between the peak amplitudes, you can see that they're still tracking the long-term changes very, very well over time. So yeah, as I guess, a starting point, we're pretty happy with this. And of course, I think both sides are going to continue to work on these methods.
Thanks, John. Thanks for your question.